Uh, Thank you very much for having me. And it's lovely to be there, at least virtually. It'd be a lot more lovely to be there in person and hopefully next year. Let's jump right in. I have some contact information. I will repeat that at the end of the session and happy for people to reach out. I want to start right off and invite all of you to $1 million lunch. Oh, yes, you're in London, £1 million lunch. And let me tell you how that works. This is a real world story, a real world use case from one of our customers. The story starts: a data scientist and an analyst walked into a lunchroom. Okay, it's not a punchline, it really is what happened. This is at a very large retailer, and a data scientist and an analyst happened to be having lunch together. And the analyst said that they could build a really great price matching feature if only there were enough time and budget to build a system that could crawl the web and collect pricing, competitive pricing data. And the data scientist said, well, that data had already been collected. It was already there for a different purpose. And they literally got up, left the lunch, went in, and within a day built a prototype. And the end AI system and analytics system working together basically generated hundreds of millions of dollars in increased revenue. This is a real story. And so it worked mainly because these two people collaborated. They talked to each other about what data they had, but because both the analytics and AI could be run on that same system, it made it very easy, a low barrier to entry, to be able to build that prototype and show that the system could work. So there's a key lesson there. It's very valuable for people from different groups to collaborate, to understand what data you have and how it can be used. And so let's go to another story. Data has value when you give it context, and context comes from understanding what it is, from talking to people with domain knowledge. But this story, the second story, has another lesson in it. And this shows why running AI and analytics on the same system can give you a second project advantage. Now, that previous example was unusual because, in a way, because the data had already been collected by the data scientist for a machine learning project, but often it goes the other way around. Data is collected for a different purpose, and someone building an AI or machine learning project sees an additional way to use that data. And indeed, it may be data that had been collected for years before the machine learning project starts. Machine learning and AI have great potential value, but they are speculative. And so anything that can be done to lower the entry cost, the entry barrier to trying those projects, because you may have to try several, payoff can be very big when they do work, but they are speculative. So that's an important way to make them feasible, to be able to try many different things. And keep in mind that sometimes the most powerful AI or machine learning is the simplest, because what matters is to pick the system that is the algorithm or model or approach that is appropriate for the system. So in this next story, this was again a customer, big industrial customer, had a lot of IoT data. This was an oil and gas company, and they were working with us to build really sophisticated machine learning and AI to analyze huge amounts of IoT data for various reasons from their various sensors in the field. But one of our data scientists working with them was also very clever to realize that business knowledge is expert domain knowledge. He was talking with some people in accounting, and he discovered a way to build a really simple additional machine learning system for a different purpose that was a quick and big payoff. In a huge company like that, there often are mistakes that are made on an invoice, a code is put in wrong, and some expense that should be reimbursed or is a tax deduction or so forth is coded wrong, and that money is lost. There are very few of those in terms of the overall number of invoices, so it's too hard manually to go through to look for them. But by building a very simple machine learning system, classification system, it was possible to actually basically reduce the signal to noise problem, to enrich the kind of potential target that a human auditor could go in and take action. And the result in this system is that they literally ended up with millions of dollars in recovered revenue. So the simplicity of the model, understanding the context, making use of domain knowledge. But this was a situation where there was a low cost to doing the project, the AI project, because it was a second project. Another example from another customer with a second project advantage, where they took advantage of existing data to build an AI project, is with a major media company. And what they did in this case is they had upgraded to a better data infrastructure that could handle really large-scale data, but they were actually doing traditional analytics. And so that was the first stage of the system. They had to build that for what they were doing. But they realized that once they had that data in place, had that data infrastructure in place, again, it lowered the barrier to trying different AI machine learning approaches. And one that they built gave them real-time insights. They were better able to predict ad volumes for advertising revenue, and by better predictions, they really increased their revenue there. So these are just examples, real-world examples, of people who do build systems where they run AI and analytics on the same system, and they're taking great advantage of that. There are a number of benefits, but some of the main ones are improved collaboration, a better overall view of data. You're not seeing siloed data even within either AI or analytics. You get a better view of data by having a unified system. You get this second project advantage by lowering entry costs, and that makes it more possible to try these different things. And so there are a number of different reasons to run these systems together. AI and analytics not only can be run on the same system, but in fact, they should be run on the same system where possible because of these advantages. Now, with these stories, it seems kind of obvious that AI and analytics can be run together, that they make good neighbors. But we found, surprisingly, that that's not universally known. Many people think that they have to be separate. And one of the places we ran into this with my co-author, Ted Dunning, who's the CTO for Data Fabric at HPE. Both of us previously worked at MapR Technologies before it was acquired by Hewlett-Packard Enterprise. We, in the most recent short book that we did this year called AI and Analytics at Scale, this was published by O'Reilly, and we even noticed that some of the editors there were surprised that we were writing about AI and analytics in the same book, and they said, but they're completely separate systems. We said, well, they're separate systems only if people are accepting limitations. They're making false assumptions. They're accepting limitations from some of their data infrastructure, some of their other technologies that limit what they can do. And if you start building on the assumption that that's how you have to work, then yes, you definitely have those limitations. But we know from real world examples, this book has about 20 examples, and I'll give you this link. You can download a copy for free. But it has about 20 real world use cases showing how systems that are built in a scale efficient way can easily support both AI and analytics, and with them sharing the same data. And so another advantage, obviously, is actually resource optimization, but that's not the only reason to do these together. Now, I don't want to make it sound like it's just totally trivial. There are reasons that people may think of these as very separate systems, and there are challenges that have to be overcome. We've already alluded to the fact that data is often not collected specifically for the AI or machine learning purpose, and so you have to know the data exists and process it appropriately. The data processing and the tools that are used for machine learning and AI can be different than those that are used for big data or for various kinds of legacy analytics. So you need a system that can use all of those different tools, a data storage and a data management system that gives you access by all of those tools. Your computational load, the pressures that are put in vary obviously for analytics, but they also, even within a machine learning project, vary greatly at different times. The computational needs during training model is different than computational needs during production when models are running and using new data. And so you need to be able to adjust to changes in scale, to deal with very large scale in many situations, to be able to do this at different locations, whether it's at the edge or on premises in cloud, wherever you need this to be, maybe even very separated in terms of geographical location. And you need a system that protects performance, where you have multiple applications running at the same time, multiple applications using the same data. But if you have a system that can do all of that, then AI and analytics not only can, but should be run on the same system to get the best advantage. Now, another reason that people may think of these as separate systems is that data scientists have very specialized skill, and that's a growing thing, becoming more widely used, more widely adopted, a kind of a new field of data engineering. There's certainly overlap between the data scientist and the data engineer, but there's also overlap with traditional developer skills. And we're increasingly seeing people who are working together in teams with these different skills. One that people sometimes overlook is it's also important to have an overlap with people who have domain knowledge, who are experts, whether it's very technical field or any business. The person knows their own business, they're an expert in that business. When you think about it, of all these different types of overlap, the biggest overlap is data. It is really, in many cases, the same data that people want to be using. And so being able to deliver, handle, storage, store, manage, move that data in efficient ways that also allow true multi-tenancy, to allow data sharing, to allow collaboration, really does make sense. So in order to be able to run AI and analytics together, you want to build what we're calling a scale-efficient system. In fact, if you feel like you can't have them coexist, co-locate, that's probably a symptom that your system may not be scale-efficient, that you may be accepting limitations that aren't necessary. When you build one of these systems, really two very important aspects or steps. You want to develop a comprehensive data strategy. That sounds like a small thing, but it has a huge impact, even changing the way that people think about data across their enterprise in different projects, in different departments, in different locations. Again, whether maybe it's at the edge, it's in cloud, it's an on-premises data center. Thinking of data across all of that as a comprehensive and cohesive thing makes a big difference, tends to avoid siloing data, and improves collaboration, improves building any of these systems, whether they are AI and analytics. And in order to do that, you also need to make sure that you're using technologies that are basically good neighbor friendly, technologies that don't impose unnecessary limitations, especially in very large scale systems. Now, two good neighbor technologies, it's really useful in these systems, in any of these systems, especially in machine learning systems, and especially where they are sharing data with other types of things with analytics. It's very useful to be able to build containerized applications. And where you have a very large system, you need really efficient orchestration of those containerized applications. Kubernetes is an excellent framework for that type of coordination. It's really beginning to lead the field. And you also need data infrastructure that basically is the parallel to that. The data infrastructure is orchestrating data. It's orchestrating data logistics, not just storage, but movement of data. It's adjusting performance to make sure that things don't interfere with each other where you have multiple workloads. It needs to be very, very reliable, self-healing, be able to handle very large scale, but literally to be able to scale up or down, mainly to offer very broad flexibility. And one of the most important aspects of flexibility for the data infrastructure is that it needs to have multi-API access. And what I mean by that is that different tools, different languages, different types of applications should all have access directly to data, including big old-fashioned big data applications, modern AI systems, modern analytics, legacy systems. They all need to have access to that same data, not where you're having to constantly copy data out of a storage pool or a big data lake into a separate system, into, say, a data science workbench to be able to do the work. We're talking about doing all of this on the same underlying system, and that makes a tremendous difference. Of course, where you have multiple groups using data, not only do you want to give broad and flexible access to different types of tools via this multi-API access, but you also want to be able to manage and protect data and data security, to have fine-grained control over who does and who does not have access. I've separately written about some of the advantages of using access control expressions, or ACEs, versus ACLs, and I'll give you a link to that. And lastly, you need a system that can handle data motion in a very efficient way, with low latency, with reliability, and at very large scale if needed. Now, the real world cases that I talked about earlier, and the ones that are in the book that we discussed, were built on what used to be the MapRData platform, has now been extended by Hewlett-Packard. It's now the HPE Ezmeral data fabric. But whatever data infrastructure you pick, it needs to have these capabilities that I discussed earlier in order to support a scale-efficient system and in order to run AI and analytics together. And this has other advantages. I'm going to give you an example here just very quickly. Let's see, I think we still have some time. A system, and this is actually based on a real-world financial services system, but systems are often built from point solutions where people are accepting limitations that they don't really realize are unnecessary from some of the technologies and tools that they're using. In this diagram, this is a workflow. You can see there are many steps. Many of the steps, data is being copied from one system to another. The dark gray blocks are literally physically separate systems, and so you're copying from one system to another, and there are also many, many different steps where one system doesn't have direct access. You have to translate it into another system. So basic things have to be done. There are many steps in getting them done, and they're being done across many different pieces. That's not only kind of an expensive approach, but it's a cumbersome and a fairly brittle approach, because when you want to make changes in that, whether it's to scale up, to add a new project, to add a new type of data, it can be very difficult to do that. And often you find in systems like this that, for good reasons, IT's first answer whenever you ask to do something is no. So a similar system, when it's built on a unifying data infrastructure, again, in this case, it happens to be HPE Ezmeral Data Fabric, but whatever unifying data infrastructure that you choose, you find that when it has capabilities that we've already talked about, that not only do you collapse it down so you don't have so many separate physical pieces, but a lot of those copying steps go away. In fact, some of the processing steps go away, and the system becomes a much simpler system. In this particular diagram, the triangles are basically a feature of data fabric, called a data fabric volume, a very good way to manage data. It's just showing you how you're landing data, moving it from one thing to another. All of these tools have direct access to the data in these distributed system, whether they're files. It also has distributed tables. It has stream events. It's all, the data is all being delivered to the applications or the tools as needed without having to make a lot of changes. So you can see what a simplification this is. And so that data fabric, that data infrastructure, needs to be able to also interact with containerized applications. It needs to provide data persistence of state for containerized applications, but to be able to do that side by side with legacy and non-containerized applications. The input from one application may be the output from a previous one. They all need to work together on the same system. Again, good neighbors wherever they're located. And remember, a lot of business happens at the edge. It's not just big IoT systems. that present you with edge situations, but I am going to talk about one that does present big situations or big data coming in from the edge, a really extreme example. But I want to show it because in taking these same issues and thinking about them in edge systems, people often focus first on how to get data from the edge back to the center, whether the data center is on premises or in cloud. And that certainly is very important. But it's also important to be able to get data back to the edge, to get code, to get models, analytics applications back to the edge, where you do some processing and some modeling actually at the edge. So again, using several of our customers as a kind of composite example, people who are doing autonomous car development are handling massive amounts of data ingestion every day. They have a fleet of cars that are collecting data. I think it's something like 5 gigabytes per second per car. Those cars are running for hours. They come into an intermediate field station and upload that data to Data Fabric. It's moved to the core only as necessary. And in many situations, this is something like 5 to 10% of the data is all that's moved to the core, even though there's very efficient data motion through mirroring or direct table or stream replication. But you don't need to move that much data to the core. A lot of the initial processing and modeling can actually be done at the intermediate edge station. And so this is how it works. It's a fairly complicated diagram, but really what we have here is at the edge, you're ingesting data, managing it through various volumes. You begin to do some feature extraction that can be stored in a metadata table. That table can be directly replicated through table replication to the core if needed. You also put some of the data, a smaller amount of the data that does need to go back to the core for more sophisticated modeling, into a transfer volume. And that's efficiently mirrored to the core. But remember, you also need traffic back to the edge. You can directly reach back to the edge from a core application and access data without even moving it. You can move data back to the core. You can move updated applications, updated code, updated models, back to the edge. And so you have traffic going both ways. It's very efficient. It doesn't matter if the applications that are moving are AI models or if they're analytics applications. They're all moving in the same way. And the logistics are being handled by the data infrastructure at the platform level rather than having to be coded in. Now, I just want to quickly close and remind you that we're talking about very extreme scale there. But dealing with scale and scalability is not always just about very large scale. There are other aspects of scale that can be surprising. Sometimes the scale you need to deal with is smaller than you expect. It may be small files, but very many of them. It may be that you have a system using smaller volume of data and it needs to interact with a large data system. All of these are reasons that you get a greater efficiency and it's easier to build these applications if they're all sharing data and running on the same system. And so just to conclude, AI and analytics do work well together. They can be good neighbors. And the tips on getting there and building a system that can do that is develop a comprehensive data strategy. Think of data across organizations and that cuts across different departments. Definitely make use of containerization so that you have a predictable environment to be able to run very different types of applications, basically side by side and in a reproducible way, and in a way that makes it easy for people who are handling security or handling quality assurance to be able to go in and test and reproduce those systems in the appropriate way. And you can deploy them wherever you need them to run. Your data infrastructure has to have certain capabilities that we've talked about in order to support this. But when it does, you have additional advantages of less siloed data, which helps across your organization, and it encourages your IT team to say yes to new projects because they know the system will remain reliable and because you don't have to scale IT to scale out new projects or new applications or growing amounts of data. The last thing is to keep in mind that to make these things really work, there's a human element. You need to develop a changing culture to really be able to recognize the context that gives data value and to look for new initiatives in data sharing. That's a whole different topic and a whole different presentation. But there's some exciting new things out there, including something called the Ag Stack from the Linux Foundation in Europe. The Gaia X is a new data initiative. There's some excellent ways that people are sharing data. And again, we're cross-cutting between things that are used for analytics and things that are used for machine learning. And so thank you very much for having me here. This is a free resource that talks about this and many other use cases in scale-efficient systems. These are some additional resources and papers that you can look at that deal with some of the topics that I've alluded to. And I think these slides, I hope, will be made available to you. If not, do please just email me with your questions and I'll send you the links. Please do continue to support women and all types of diversity in technology. This is not just good for the individual, it's also really good for society. And from one woman in tech, I say thank you very much for having me here today.
Thank you so much, Ellen. I don't have any questions on Slido because these guys are reticent about asking questions, but they're all listening agog. And I think there's a lot of excitement when you say you're going to share the slides, because that seems to be the key thing from everyone today. And just apropos of the women in tech, you have to queue for the cloakrooms here, which is a good sign. So there's a lot of women queuing for the bathroom. So that means that we're certainly seeing many more women at these events than normal. So